Okay, welcome to lecture number 45. We have been discussing about the Lagrange points. So, in that context, we will look into the Sun Earth system very briefly, because already we have discussed about the Earth Moon system. Accordingly, the Sun Earth system is there. So, here in this case, if you look into the Sun is located here and the Earth is located here in this point. So, here is your Earth and the Sun is located in this point. So, L1 point, it lies around 1.5 million kilometers from the Earth on the left hand side. So, this is your 1.5 kilometers, 1.5 million kilometers, or 1.5 into 10 to the power 6 kilometers. Similarly, on the right hand side, the L2 is located at around 1.5 into 10 to the power 6 kilometers, and this you can compute all the distances already I have listed here. So, using these distances and the mass of the Sun and mass of the Earth as it is mentioned here. So, these details are given here. So, using these details you can work out these distances. So, there have been mission, though the L1 and L2 are unstable points, but mission has been sent to see the Sun is here and the Earth is located here. This is your point L1. So, mission has been sent to this point where perpendicular to this line joining in the orbit. If you look like, so I have drawn the orbit like this, but if you see, I will rub it out and if we look from the side. So, if this is your L1 point, so the orbit, this is the side view of the orbit, okay. And if you look from this point, so orbit will appear like this. So, at L1 satellite has been sent and satellite orbits around L1, though the point L1 is unstable, but by orbit keeping you can keep the satellite here in this place. This is your Earth, this is Sun and this is Earth. So, a mission called SOHO was located at L1, okay, in an orbit. Of course, this has to be maintained it because it is an unstable one. So, it will not stay there, but mission has been sent there and this is the Sun observation satellite. So, for the study of the Sun, this has been used. Similarly, the satellite can be sent here to the L2 point also. So, if your L2 is located say here in this point, L2 is located, then the same kind of orbit can also be placed on this side. But if you have on this side the L3 is located, so this is of no use, because this will get eclipsed by the Sun. Okay. And any satellite, if somebody tries to place here at L3, this will be of no use. So, L1 and L2 have been used for locating the satellites and observing the behavior of the Sun or the studying the Sun. Now, we will look into the Jacobi integral we have derived earlier. In the normalized form, we once we put omega equal to 1. So, we got the normalized form. Otherwise, in the non normalized form we have written it like this. So, how the Lagrange points they emerge from this equation can be studied. This is basically an energy equation. In synodic frame. Now, V square, this is a positive quantity which is always greater than equal to 0. So, this implies that x square plus y square on the normalized scale, if we write, this will be always greater than equal to 0. It cannot be negative. And this quantity also we have written as phi minus c, this is greater than 0, where phi is a function of course, here in this case z is not appearing, because it gets reduced to a planar case as we have discussed earlier. In this point the z is not appearing, this is what I mean to say. Now, this is the equation of a surface. Okay, so, it says that if V square is always greater than equal to 0, because it is a positive quantity, at best it can be 0. So, that means your particle is not allowed to cross the surface. Say, if I have a surface and if on this surface V equal to 0, means phi equal to c, this is indicated by so then this surface cannot be penetrated. You cannot go from this side to this side until unless it is allowed. So, this we are going to study, and from this how the Lagrange points they emerge, okay, that we will look graphically. So, one thing we have I will remind you again and again, that if we have two masses, one primary mass m 1 and the secondary mass m 2. So, the Lagrange points are located in the plane of the orbit. Okay. So, if this is rotating like this about this point, this is the orbital plane of the m 1 and m 2. So, the L 4 and L 5 are located like this, L 3 is located on this side, L 2 is located on this side, and L 1 is located here. So, all these are coplanar, while here in general this is R 1 and R 2. As you remember that R 1 we have written as x minus x b 1 square plus y square plus z square, and R 2 we have written as x plus x b 2 square plus y square plus z square. So, phi is not a planar surface, it is a 3-dimensional surface, but using this we can get to know that okay, there are certain points to which let us write here on this side phi this equal to C, to which this will get reduced as the value of C is changed. Where C indicates energy of the system in the synodic frame. This stands for total energy in the synodic frame. So, phi minus C, this is always greater than equal to 0, and let us say case 1 we start considering case 1, and C is equal to C 0 is very large. And how it is possible? If we look here in this equation, so this is possible by x square plus y square becoming large, or R 1 tends to 0 or R 2 tends to 0. In either of the three ways, it is a possible. So, if we look from that point of view, okay, see here in this case, this figure has been taken from the reference Archie-Roy. The astrodynamics by Archie-Roy. Already I have given names of all the books. So, here this is showing your C 1 in this point. You can view the cursor. This is your C 1. So, this is one of the surface being shown here. Inside this you have the points 1 minus mu star written here and mu star written here on the right hand side. Okay. So, on all these surfaces you the C equal to C 1 has been written, okay, and this circle is shown larger, and on the right hand side the circle is shown smaller. What is the reason? This is all not a circle, but almost a circle. So, we can consider it to be a circle or some oval shaped. Okay. Similarly, here if you see in the figure B, so in the figure B also if you look, C equal to has been set to C 2, okay, and then the size of this surface it grows and then it merges somewhere, and here the point has been written as L 2, but this point where it appears we follow this point as L 1. We do not write this as L 2, but rather as L 1. L 2 we have taken on the right hand side of the mass mu or mu star. Here mu is referring to the M 2. Okay. So, this has got a different notation that book. So, but the figure is okay. The only thing that the notation we have to change. Thereafter, you can see that as the value of the C is changed. So, this the two inside the white surfaces they merge, and here the L 2 is appearing. So, L 2 is already there, but now the two surfaces merge, and you can see that some doll shaped of things it has appeared. Okay. Similarly, the L 3 which is being shown here, this is actually L 3 here in this point, as you can see I am shadowing it. So, this L 3 is our L 2, not L 3 here. L 3 is on the left hand side for us, and here what has been shown as the L 1, this is our L 3, okay, and what has been shown as the L 2, this is our L 1. and what has been shown is the L 3, this is our L 2, and L 4 and L 5 similarly they emerge here in this place. So, we will discuss this how all these points they emerge from this the equation we are using. Okay, so, we have been discussing here about that. So, once C equal to C 0 is very large. So, as I stated, this is possible if R 1 tends to 0 or R 2 tends to 0 or x square plus y square, this tends to infinity. So, I will show it like this. We have point here, I am showing it as spherical for convenience. Okay. So, this is one surface I am showing here, and another surface I will show by a smaller size. M 2 is located here, M 1 is located here, this is your R 1 and this is R 2. The question is why I am showing this R 1 to be larger and R 2 to be smaller. This will be evident from the equation we are using. C equal to this quantity we have written. Let us say this R 1 tends to 0 and R 2 is having certain finite value. So, at that time we can ignore these quantities, because once R 1 tends to 0 you can see that this quantity will become very large. So, if C equal to C 0, this corresponds to 2 minus mu star divided by R 1 square. So, R 1 2 minus mu star divided by C 0. So, if C 0 is very large, you can see that R 1 tends to 0. Okay. Now, along the same line we can write R 2 equal to 2 times mu star divided by C 0. So, if we do that, immediately it will be visible why R 1 and R 2 are shown with different size of the sphere or the circles, whatever you say. Reason is mu star is less than 1 minus mu star. We have taken M 2 to be a smaller mass. So, immediately you can see that the R 2 will be less than R 1 for that reason, and therefore, we show it by a smaller circle. So, here this is C equal to C 0 and region inside it is a forbidden. In this region no particle can exist. So, somewhere your L 3 is located here, L 2 is say located here in this point, and L 1 is located in mid between somewhere in this point. So, if you have this kind of configuration, so these are the shown by this blue shaded portion. So, it is not possible to go from this one to the bigger circle to the smaller circle. So, there is no communication, you cannot go from send particle from one circle to the another circle. Okay, next we and this is your R 1 R 2 and also we should show this is corresponding to x square plus y square. Once x square plus y square becomes very large, so in that case R 1 and R 2 can be ignored in this equation and directly you can see that x square plus y square is represented by C. When C is decreased, so let us say C equal to C 1 which is less than C 0. So, this can happen if in your equation for phi this can happen if R 1 goes up, R 2 goes up means increases, and therefore, C will decrease or x square plus y square goes down, this decreases. So, under these three conditions you will see this to happen, and along the same line we can work out this. So, here in this case this circle becomes large, this circle also this becomes large, this is M 1, M 2 is located here, L 1 is located here, on this side you have L 2 and on this side you have the L 3 located, as I have shown in the previous figure, that the figure from the Archie-Roy what I have shown. So, this is how this comes into picture. So, whatever we are showing here, see you can consider this to be the cross section of the surface and this is how it is visible. Okay, and then here we will write C equal to C 1 which is less than C 0. This also on this you have C equal to C 1, C equal to C 1 on the surfaces. So, here your x square y square this has shrinked. So, from the distances we are taking from the barycenter somewhere, if this is a bigger mass. So, barycenter, let us say this distance we are taking from barycenter, because x and y has been written from the refer to the barycenter. So, this is your point B which we have written as the barycenter and this is then x square y square. The same is also applicable here in this case. So, your x y square, this is x square y square, x square plus y square, this decreases, this goes down, it shrinks. So, the outer surface is shrinking and the inner surfaces are growing up. In the next level, in the case 3, as the value of C is further decreased, so now these surfaces they touch each other. This is the location of the L2, L1, okay, and L2 is located somewhere here, and L3 is located somewhere, let us say in this point. Here this is your R1 and this is R2. C equal to C1 we have taken there. So, this is C2 is less than C1 less than C0, and the forbidden region is just shaded by the green line. This is the forbidden region. So, once the C value is further decreased, so the R1 and R2 they go up and x square plus y square this goes down. So, this surface shrinks, this shrinks. While these surfaces they expand. So, R1 and R2 these are going up and x square y square quantity this goes down, okay, and as a result your L1 point manifests. Now, thereafter we further decrease the value of the C, then the two surfaces they merge like this. So, L1 is located somewhere here and then two surfaces has merged, L3 is located here in this point. So, this is your L3, L1 is here and L2 is just being is about to manifest, and outside you have this covering. So, on this you have C equal to C3 in this case 4. So, this is as a result of R1 going up, R2 going up and x square plus y square this is going down. So, C equal to C3 is less than C2 is so, because of this it has shrinked and this is the forbidden region. Now, you can see that the masses are here, this is your mass M1 and the mass M2 is located here. So, the movement can take place from mass M1 to M2. This is not forbidden region, that shown by the pink color is the forbidden region. This is forbidden region. This is point L2 about to manifest. Okay. So, if we keep on doing this iteration, okay, then the all the three Lagrange points will manifest one after other. So, refer to the figure, the graphics I have shown already from the Archie-Roy. So, L 2 now manifest here in this point, and L 3 is about to manifest. Now, it is on the curve itself or on this surface itself. Mass m 1 is located here, mass m 2 is here, and L 1 is located here in this point. So, size of the circle has further diminished, though I am not showing by the same kind of thing. You can refer to that figure or refer to the book by Archie-Roy. On astrodynamics. So, this is your forbidden region. Now, C equal to here, earlier we have taken C equal to C 3. So, again the R 1 has further gone up, R 2 has also further gone up, and x square plus y square, this has gone down. In the case 6, L 3 comes here in this point, so this is the location of the L 3. Now, it has come over the surface, C equal to C 5 is less than C 4, mass m 1 is here, mass m 2 is here, L 1 is located here, L 3 has come here, and the point L 2, this has opened up, means the point L 2 is also accessible. Okay. L 2 is just accessible, now here it is opened up. So, in this open area, this is the hashed area is forbidden area, this is the forbidden area, rest other area it is accessible. So, this part opens up. Okay. So, as the value of C is further decreased, as C further goes down. So, then what happens? Your mass m 1 is here and mass m 2 is located here. Point L 1 is located here. So, as you see in the previous figure, this figure will start shrinking, instead of like this, now this will shrink like this. This part also, as you increase the value, decrease the value of the C. So, this will further shrink, and thereafter further decrease, this will further shrink. Okay. So, as you keep decreasing the value, so ultimately the point L 4 and the point L 5, they will manifest. So, this is what I was trying to show here. So, as you further decrease, so you have the L 4 and L 5 points coming into picture. On this side we have L 3, on this side we have L 2. this is L4 is has started to manifest, is about to manifest. So, finally, in the case 8 we conclude this. So, we have mass m1 and mass m2 located here. So, your point L1 is located here and L3 obviously here if you see it is being shown here, but it is not true that it is located, as we know this will be located in at the vertices of the equilateral triangle. So, I will shift it little bit here in this point and so like this. So, this is your L4 and here this is your L5. So, finally, your L4 and L5 they will manifest over the vertices of an equilateral triangle. On this side you will have L2, L1 is already here in place, and on this side we will have L3. So, this way all the points are now available to move from one point to other point. So, the phi which we have written as x square plus y square 2 times 1 minus mu star divided by r 1 2 mu star divided by r 2 equal to c. So, that means phi equal to c, this is also called the Hill's surface. Or the Hill's limiting surface, because this surface cannot be penetrated, cannot be crossed. Okay, so, we will conclude this chapter lecture here, and in the next lecture one more lecture I will devote to the issue of Lagrange points, because whatever we have discussed it is all about the stationary Lagrange points. In the synodic frame they appear to be stationary. Okay. These are the stationary solution. As you remember, we have written it by the solution we have got by putting x double dot equal to y double dot, z double dot equal to 0 and x dot equal to y dot, z dot equal to 0. So, in the synodic frame this is the situation, but if we look in a for a dynamic solution which we call as the generalized Lagrange solution. So, the generalized Lagrange solution is also available, it was developed by Lagrange. Okay. So, there the shape of the triangle it will remain the same, but the size of the triangle will change, it may contract, it may expand, it may oscillate. Similarly, the linear solution, where the linear solution we have looked at the L1, L2, L3. So, in the stationary solution these are the fixed points in the synodic frame, but in a generalized solution these points are not fixed, rather the ratio of these points they remain in actually they remain in the distances between the points, they remain in a particular ratio, which I will describe little bit in the next lecture. So, I will devote one more lecture to this, and then we will wind up this chapter, because time does not permit we very limited number of lectures where only 5 lectures were meant for this year discussing the Lagrange points, but we have taken a lot more than that. So, in the next lecture I will wind up this particular issue, giving you little bit of introduction to that topic, and handout I will supply, in which you will get all the details, all the mathematical conclusions, how the points L1, L2, L3 they are unstable, and L4 and L5 they are stable. So, all those things will be discussed in those handouts. So, wait for the course to start. So, at that time we will get all those materials. Thank you very much.